So, hello everyone. I'm here to talk to you about modules and modularity, and as you can see, I've shamelessly stolen this title from Jane Austen, but if it's good enough for her, it's good enough for me. So, as Olaf said, I am the CTO of Paremus. I'm also the chair of the Internet of Things expert group in the OSGi Alliance, and I work in open source. I'm a PMC member for Apache Aries, and I'm also a BND Tools hacker. And I have a book, which I'd like you to read, but I'm not going to say anything more about. So we're here to talk about modules. What do we think a module is? It's a pretty fundamental question, and I'm sure we've all got an idea, but the problem is that modules, they're a lot of things. How long have you got? If we were trying to discuss modules, I could easily fill the half hour with this one slide, because this is a module. For those of you who have an espresso machine, this is also a module. Modules that you put in to give you your coffee, much like the very good coffee we've got outside. The thing is that this is also a module. It's in fact built into the name. They call it the LEM, the Lunar Excursion Module. So obviously, these aren't the things we're going to be talking about. We're going to be talking about modules in software, because we're here because we write software. And the thing is, a software module does actually share a lot of things in common with all of those other kinds of modules. It's not that software is so completely different. So it's basically a piece of a program that is going to do something, but it's only going to do one bit of something, and it may interact with other modules that are then going to do other bits of it. So it's about encapsulating this function so you can reuse it. So you can take this module and maybe use it with some other modules, or maybe use it on its own. grep is really useful, but grep is even more useful when you can combine it with things like cat. And when it comes down to it, what you're really talking about with modules is the fact that you don't need someone to build something specific just for you. We don't all have to go and say, I need to write my own search utility. I need to build my own CPU from transistors. I can buy one, and I can buy one from Intel, or I can get one built by AMD that fits the same socket. And that's the important thing. That's what modules give us. So just talking about, we've got these modules. How did we get here? What was the reason that we created these? Well, so a Boeing 747, we think of that as a fairly big unit of stuff. But actually, a 747 has lots of things in it. It has, in fact, 6 million, or thereabouts, number of parts. So 6 million different pieces go up to making one of these things. That's including rivets and stuff. So, that's how you get to such a big number. And of that, you've got 171 miles, or because I've come across into mainland Europe, 274 kilometers of wiring, or 8 kilometers of tubes, just for moving fuel around, or air ducts, that kind of thing. And it took 75,000 drawings to build this thing, and this was all done 50 years ago. You think of a 747 as a modern plane, it's really not. It was 50 years ago that they designed this thing, so all of these drawings were actually done with pen and paper, and then digitized, because they didn't do digital design at that point. So you can see that we've got all of this stuff. And it's why we need modules, because there's no way that you could build a system like that if you were having to design every single seat in the plane individually. If you had to redesign the wing because someone changed one of the engine components, that would be really bad. So this is why we have modules. This is why a 747 works, and it's because the engine is a separate unit from the wing, is a separate unit from the fuselage, is a separate unit from the rudder. So if you need to tweak one of the bits, you don't have to change the whole of the rest of the plane. So obviously, a 747 is a big, complicated machine. I think we'd all accept that we probably don't individually have the skills we would need to build an entire 747. It may be that in this group we've got enough skills, but one person couldn't do it. So it's too hard, and that's why we need modularity. But software is harder than building aeroplanes. I'm going to say that to you now. Building a big software system is harder than building a plane. So I've got a little quiz for you here. How many lines of code do you think it took to land the NASA Space Shuttle? Anyone? Sorry? 500,000. Someone's been doing their research. It is indeed 500,000 lines of code. OK, so given that that can land a space shuttle, how many lines of code do you think there are in a DVD player? Higher or lower? We'll go with higher or lower. So a couple of highers, couple of lowers. It is, in fact, twice as much. It's 1 million lines of code. Now, Windows XP, any guesses? Windows XP is 40 million lines of code. Now, Windows Vista, they added 10 million lines of bugs. In a BMW 5 Series, so this is a car, you don't necessarily think of that as having a lot of software in it. There are actually 50 separate networked computers talking to each other. So these are horrendously complicated systems. You may think that making the engine is difficult. Making the computer software for that car is much harder. And anyone been reading the news? Because until quite recently, I'd have finished there as, that's really big and complicated. But someone recently leaked the number of lines of code in the Google code base, which, can I just tell you, is all one code base. And 2 billion. It is 86 terabytes of source code. And here is a company that needs modularity. So we've been talking about modules, and modules are these things that we need to build. Now, given what we do, I'm assuming most of us are writing Java, so we're probably using Maven, because Maven is very popular. And there's a quote that I love, which is, if it's not in Maven Central, then it doesn't exist. And that is literally true for many projects. They try to release something, and until it goes into Maven Central, people say, I couldn't find your release. It's like, but it was on our website, you can download it. It's like, no, I couldn't find it. I looked in Maven Central, and it wasn't there. So Maven is really important to our industry, if only because it provides the place where you go to find everything. And things that you put there are, in fact, called modules. If you look at Maven terminology, the projects, the leaf nodes, are called modules. So they've got to be right. You wouldn't call them modules unless they were. And actually, they do show some of the properties that you need in order to be a good module. So they have a well-defined name and version. So that's your gav. You can use that to find the thing. And it's independent of the file name, which is really important. It's one of these wonderful things, being able to divorce your identity from what someone chose to call the file on disk. Because there's nothing more annoying than someone changing a character in the file name, and then the whole of your system stops working. That's pretty bad. Unfortunately, there are still a lot of tools that rely on the fact that your file name is something like groupid.artifactid-version.jar. And people are bad. You shouldn't do that. Has anyone here read a book called Sophie's World? A few hands. So it was really, really popular in the 90s. It's a bit less so now, but it was written by a Norwegian, and it's basically a book about the history of philosophy. And this is our little philosophy interlude, because you're probably all bored of me talking about modules already. But the important thing in this book is that Sophie is learning about philosophy through receiving letters in her postbox, and she doesn't know who's sending these letters, but they have these philosophical questions. And there's this really good question, which is, why is Lego the most ingenious toy in the world? What makes it the best toy? And does anyone know the answer? So the answer actually relates to an atomic theory from Democritus, who was a Greek philosopher. And it's basically because you can build anything with Lego. It's the best toy because you can turn it into every toy. That's the idea anyway. And it is true, Lego do have some pretty awesome toys. I don't know if you know much about these, but these are 3 of the 4 biggest Lego sets you can buy. There's the one which is Tower Bridge in London. Obviously, we've got the Imperial Star Destroyer. In fact, no, that's the Super Star Destroyer and the Millennium Falcon. In case you haven't been able to tell so far, I'm really cool, and Lego is cool too. But the problem with these sets is you get something called the IKEA problem. I'm sure you all know IKEA. So how do you turn this pile of pieces into, well, maybe a Super Star Destroyer, or maybe it's just a bookcase, but you've got a pile of pieces, and you're trying to work out the instructions, but it turns out that they're in a language that you can't read. You can't even read the script for it, because it's not in Roman script. And this gets kind of difficult. It also, you then find out later that the reason you couldn't do it was that some of the screws were missing. And you end up like Grumpy Cat, because you're very sad that you weren't able to build this thing in the 3 hours you allotted for it on your weekend. So how do we solve the IKEA problem? So you can use brute force. So with enough time and money, you can build anything. So I don't know if you're aware of this, but someone actually built a real human-sized house out of Lego. This is it. You can see they made it nice and stripy, so they kept all the colors going round. So rainbow house. And this is them about 2/3 of the way through building it. It took 2 weeks to build. It may not sound like a long time. Actually, you're probably thinking, why aren't we always making houses out of Lego? 2 weeks would be brilliant to build a house. Would you care to guess how many people were working on this house? Do we think more or less than 100, higher or lower? So more than 100. Do we think more or less than 500? The answer is there were 1,200 people working on this house for 2 weeks. So when you multiply that up, you find that it is a colossally scary number of person-years of effort. In fact, if it took that many people to build a normal house, then most of us would be homeless. And the reason that it takes that long is that it takes 3.3 million Lego bricks to build a full-size house. And the way that they actually put it together was most of these people spent their entire day building super bricks out of 272 normal Lego bricks, which are basically real bricks that you then use to build the house. So whenever you think that your day job is boring, just remember that people volunteer time to build bricks out of bricks. So as we've learned, modules aren't enough. Lego gives us this great opportunity to build stuff, but without instructions, it's really hard. And it turns out that Maven Central is this amazing box of Lego, but it doesn't have any instructions at all. So you go and you look, and it's like, great, how do I build something? And it's really hard. It takes a huge amount of a priori knowledge. So building anything big is hard or even impossible. So what we need is we need to be able to search for stuff in Maven. And this is where people will put up their hands and say, but I go to search.maven.org and I can type stuff in and I can find it. But the problem is, you actually can't really do that because you've got to search by name. So you already need to know what you're looking for. You need to say, oh, what I need right now is I need the H2 database, so I'm going to search for H2. Or I need the Zookeeper client, so I'm going to search for Zookeeper. But you've already made that step to say, I need Zookeeper, or I need H2, which means you have to know what those things are in advance. So this is where we come to something called the modularity maturity model, which is where we learn that modules and modularity are not the same thing. They are related, but they're not the same. Because modularity needs more than just a name. So you can see here we've highlighted on the modularity maturity model the 2 different things that we're interested in. And you start with basically nothing, my lump of code where some horrible developer has written the entirety of their application in one class, possibly even one method. Did you know that there's a limit on the number of lines you can have in a Java method? Because if you do, then you're one of those developers who I think probably needs their credentials taken away. You shouldn't be allowed to commit anymore. In case you're wondering, it's an unsigned short. You can have 65K lines of, 65K byte codes, not even lines of code. But don't ask me how I found that out. So the difference between modules and modularity is that your module needs to have a contract. That's the thing that separates modularity from modules. It's not enough to say who you are. You need to say what you provide. And crucially, the contract goes both ways. It's not just, this is what I provide. It's, this is what I expect from the world around me. Think of it this way. If you plug in your DVD player into your TV, you're expecting that to work, because there's a defined contract for, I'm going to produce a signal which is going to have this frequency and it's going to phase in this way, and that's how the TV is going to determine the picture being sent by the DVD player. And that's fine. So you think of the contract going one way. On the other hand, if the TV says, that's great, and I'm going to draw 30 amps while I'm doing it, you're probably going to blow up your DVD player, because the DVD player was never designed to give you 30 amps. It was thinking maybe 100 milliamps tops. And that's where the contract cuts both ways, because it's one thing to say, you're going to provide me with this signal, but you also need to say, and I promise that I'm going to do my part and I'm not going to consume all of the current and blow you up. And the same thing is true in software. You say, I provide this API, but I'm also going to depend on these other APIs. And unless you say both of those things, then you're building a brittle system that may blow up in your face. And this is where we really need our modules to be self-describing. So you've got these things, and they're called requirements, and they're called capabilities. So for a jar file, we want the name and version. Maven got that absolutely right. Named modules, where the name is independent of the file name and the thing is versioned, are really important, and they are a necessary first step. But we need to keep going. We need to add code dependencies. We need to know what they are. They need to be written down, and they need to say what we need, not where we need it from. And the reason for this is simple. You may have been thinking, but Maven has this dependency section. I know my dependency graph. But you're declaring dependencies based on what you depend on, where you depend on, not what you depend on. You say, I need this version of log4j, not, I need someone who can give me the log4j package. Which means it's really hard to assemble things at runtime when loads of people are needing subtly different versions of stuff. You end up having to write all of these exclusion filters for all of... Anyone here had to write an exclusion filter in a Maven POM? So quite a few hands going up. Well, I want you to know that every time you write an exclusion filter, a modularity fairy dies. So you need to fix this problem. And the important part is, if we're going to say, I depend on this stuff, you also need to know what stuff you provide to other people. Because that allows you to encapsulate. It allows you to say, I may contain this, but it's not for you. So the Maven Shade plugin is a really good example of people deliberately doing this. You actually move stuff into a different package namespace so that you're not worried about, oh, someone might try and depend on me for this thing. If you make an explicit list of, these are the things that you can consume from me, and people make an explicit list of, these are the things that I need from outside, it's very easy to match those up. And it's also really good because you can build a system where you know that you're using things people intended you to use. And for those of you who hadn't noticed, what we've actually just done is we've built an OSGi bundle. This is all OSGi does. People think of it as a big, horrible, complicated system. And it's actually not. At its heart, it's very simple. It's basically just a jar file which lists the things it needs and the things it provides. It's really simple. And what this does is it means that every single module has its own instruction manual. So you know where in the model your bricks fit, and also which other bricks could do the same job. Because it's one thing to say, OK, I need a brick that goes in here, but if it has to be exactly that brick from the big pile of bricks, it's going to take you a long time to turn your pile of bricks into your Millennium Falcon. It sometimes just doesn't matter. You just need one that's the right shape. And the benefits that this gives us is it means that we can say goodbye to things like class not found exception at runtime. Because we know, we said, I depend on this stuff. And therefore, if the stuff's not there, you're not going to start the runtime because you're going to look at it and you're going to say, oh, yeah, I have not got that thing that it says I need. You also get completely decoupled from your implementation because you're saying, this is what I need, not where it comes from. There's no chance that you're going to accidentally end up always having to deploy with Jetty rather than Tomcat, or Tomcat rather than Jetty, because all you're saying is, I need something that's going to be a servlet container and copes with this level of the servlet API. And that is also how we get to the complete loss of these leaky abstractions. You know, no more of foo impl gives me this internal method which I really want to call, because the chances are that the person who wrote the foo impl didn't intend you to call internal method 0. But that's not really enough to make our system truly robust. Just listing these things isn't enough. Because we need to give information about the version of the stuff that we're providing. Versioning by module, once you start depending on what rather than where, isn't enough. Because you can't say, I need the servlet API from the servlet API bundle at version 3.1. You're saying, I need the servlet API. And the person who provides it needs to tell you what version that is, and it's not going to be the same as the version of their bundle. Just won't be. So what we need is we need to have our versioning scheme, and we need to say something about what it means. So I think most people can get on board with 1 going to 2 means I've probably made a breaking API change. And most people can get on board with I've changed the final digit in my 3-digit version. And 3-digit versions are pretty much the standard. I know Maven doesn't enforce it, but everyone I know uses 3-digit versions. GitHub recommends 3-digit versions. So the top and the bottom one are ones that people find uncontentious, although the one that's more interesting is the 1.x to 1.y model. And this is a backward-compatible API change. But the important thing is to recognize that backward-compatible API changes are not backward-compatible for everybody. So when they changed from Servlet 3 to Servlet 3.1, they did not break anyone who wrote a servlet. But they sure as hell broke Jetty, because Jetty needed to implement the new methods on servlet context. So you've got to be aware of who your API is being consumed by to know what level of things are breaking and who they are breaking for. But if you do this, someone who uses the API can accept a range of versions, which is nice. And this model is called semantic versioning. This wasn't invented by me. It wasn't invented by OSGi. Well, OSGi has a white paper on it. There's also a thing called semver.org, which is set up by the founder of GitHub, which actually lists these rules as something that they found to work really well on GitHub projects. And the thing about semantic versioning is it lets you predict the future. You know when someone has made a change that stopped you working. And you know, even if they made that change after you wrote your application, you know that you're no longer going to work. And that is a level of power that most people aren't used to. They're not used to knowing, oh, it's safe to do this thing. I can upgrade to that version of this library. Most of the time we do it in hope, but you never really knew before. And you can actually use tools to automate this semantic version management in your code. So there's BND tools, there's a plugin in Apache Aries that does semantic versioning work. And you actually get a build failure when you forget to change your version. It will analyze your code, it will see the methods that you've changed, and it'll say, OK, you need to update that particular version by this much, or by at least this much, in order to be safe. So that's a lot about modularity at a code level. But one of the other things it's really important to do is to keep things loose. Because we've encapsulated everything, but once you've encapsulated things, how do you share anything? Because if we've got these exports, but we've got implementations that we don't want to share, how do people load that type? So the new operator, which is the way that we've all learned you shouldn't do it, way, way back, no. But the factory pattern, which is the way that we were all taught you should do it, is actually still a tight coupling because that factory needs to be able to find that particular implementation, at which point you're then saying, OK, I can only get that one implementation from this factory, and what if I actually need that other implementation from over there? What we really need is we need microservices. This is exactly what microservices are for, loosely coupling modules. They allow you to have a pure API dependency, and all you've got to do is find the thing. It builds into your architecture the fact that all of your modules are loosely coupled. But microservices, they cost, right? They are popular, they are lightweight. But if you made every single interaction a microservice interaction, wouldn't it be awfully slow? I mean, that's probably what you're mostly thinking, right? Except those of you who are in DevOps, because you're probably thinking, how on earth do I manage all that configuration? And I don't blame you. It would be a nightmare if every single object interaction had to go via an HTTP URI and you had to know what that URI was. It would be hellish to try and make that work. But you can have in-VM microservices. OSGi does it. There are other platforms that have effectively a service registry in the virtual machine. And you've got this registry of services and actually notifications of when those services become available and when they go away. And you can build this self-assembling runtime. You share the services via this registry, and you no longer need to know anything about the implementation type or how it's constructed or what it depends on. You've just got this really nice encapsulated thing that you're going to use. And you didn't have to configure it either. It just came for free. Also, in the case of OSGis, and most of them, there's zero performance overhead, because actually once you've wired the things in the first place, you're just doing a normal method call. It's the same as invoking any object. And the best thing is, it's turtles all the way down. You may think about building your microservice to expose to the world, but wouldn't it be great if your microservice was built of microservices? That way, you can start making changes within your microservice in exactly the same way that you can make changes within your business by changing your microservices. So what I've learned in years and years of writing big software is that modularity is the only game in town when it comes to making your big software project actually work. Because most of us don't have the luxury of having 1,200 people to throw at a problem. And even more than that, we don't have the luxury of having a problem you can throw 1,200 people at, and it will go 1,000 times faster. Most of the time, you've got the law of the mythical man-month, and you throw 1,200 people at it, and you spend 2 years just trying to work out the project hierarchy. So nobody goes out there intending to make their big software project a monolith. But it will happen unless you actively try to stop it. And if you start with the right tools, it's really easy. It's even possible to take something that wasn't written the right way and to change it. But be warned, you will learn things about your code base by doing this. Your baby, it may be your baby, but it's not always as pretty as you thought it might be. When you look really close, when you start trying to massage it into a modular baby, then you'll find there are some pretty ugly things underneath that nappy. I'd just like to say a quick thank you, obviously, to the places I got the images from, and also to Graham Charters from IBM, who was the guy who first came up with the modularity maturity model. And I also want to say that, obviously, we're here in Darmstadt now, but Liferay do have a symposium coming up in North America, in Chicago, and they're actually hosting OSGi certification exams, and there's a discount. So if you're going and you're interested in this stuff, you've got enough time to really bone up on your OSGi and think about going and getting certified. So you too can go out and tell people about how to make your projects really modular. Well, thank you, everybody.